So it's a pleasure to have PPerlekar, who's, I think it's the first time in the festival. And Prasad is, I think, well known for his work in statistical mechanics, turbulence, fluid dynamics, and complex systems. He did his PhD at the Indian Institute of Science. Was a student of Rahul Pandit, who will meet if you haven't already next week. And now he's on the faculty of Tata Institute for Fundamental Research in Hyderabad. And today he's going to talk about something different for us, named turbulence in bubbling systems.
All right. So thanks, Pat and Guillem, for the kind invitation. I've thoroughly enjoyed, though a bit overwhelmed by the complexity of plasma physics. And so I look forward to learning more. But I think maybe they decided that, after all the intense talks, it's a good time to have a more relaxed talk, which is much more easier. So I'm going to talk about one such topic. And the topic is, as you see, the way the title is, it's very easy to state. And I will show you what the system is. And but as we realize, so I started to working on this topic as with a project student, and soon it turned out into a massive problem on which I've been working for past 10 years. And you would see why it's so interesting. And let's see. And what I'll try to do, at least that's the intention, that I'll try to make the talk as much student friendly as possible. And both Diff and Pat, told me that the talk you should ask questions to students. So let me start by doing that. And let me ask the following question. How many of you who are the students have heard homogeneous isotropic turbulence? This name, how many of you have heard? Okay, and how many of you have heard Kolmogorov scaling? So there are quite a few who haven't heard either homogeneous isotropic turbulence or Kolmogorov scaling. And because most of this talk is going to be about that, maybe what I should do is I should start by giving a zero-level course of turbulence or homogeneous isotropic turbulence. Okay, so what we are thinking of, so when I talk of turbulence, unlike many of the talks which happened in previous days where there were boundaries, there were these intense structures coming out of boundaries. When I am thinking of turbulence, it's a very, very simple view. The view is the following, that you have a system in which you are applying forcing at some scale, right? And then somehow the energy gets transferred to smaller and smaller scale via nonlinear transfers. And eventually, at small enough scales, it gets dissipated by viscosity, right? That's the simple picture I have. And this is where Kolmogorov was amazing. Because what he came up with was the idea of self-similar theory of turbulence, where one says that in the limit of vanishing viscosity, note, I'm not saying viscosity is equal to zero, but rather I'm saying vanishing viscosity. Having finite viscosity is important. So in the limit of vanishing viscosity, if you look at velocity increments, so you take 2 points in your fluid, right, separated by a distance r, and you look at the velocity increments across those 2 points, then any order p velocity increment would scale so that energy dissipation rate to the power p by 3 and the separation to the power p by 3. Okay, and this you can prove by a simple scaling analysis. And in particular, what many people look at is the second order structure function, which is velocity difference squared. And that typically scales as epsilon to the power 2/3, r to the power 2/3 in this simple theory. And correspondingly, energy spectrum scales as k raised to minus 5/3. And I don't think it's very much visible here. Maybe it's visible on that screen. That if you look at the second order structure function or second order velocity increments over several decades, this scale is r to the power 2/3, right? So that's the picture. And the way Kolmogorov came up with the idea was the following, that if you're injecting energy at large scales, the picture here is representation of an eddy or a flow structure. Don't ask me how you identify an eddy, I don't know. but that's what people typically think, that there is a flow structure, some large scale flow structure, right? Victorian, in each stage, this eddy is getting broken into smaller eddies in a self-similar way. And while this process is going on, what one assumes is that energy flux is maintained constant across. All right. So you inject some energy, it goes from one scale to other scale to other scale while maintaining constant energy flux. And eventually you go to small enough scales where it gets dissipated. Okay. That's the picture. And then, the genius of, so you can check that experiments actually figure out that it works very well. You have a beautiful several decades of pi-third scaling in the spectrum, which is nothing but the Fourier transform of second order structure function defined so. And the genius of Kolmogorov was that he went ahead and proved an exact relation. And more or less, at least in homogeneous isotropic turbulence, this is the only known exact relation, where one shows that the third order structure function, third order longitudinal structure function, scales as -4 epsilon L. L again, here is the separation between 2 points. Now, what is exact about it is the factor of 4/5, right? The scaling theory would have given you that the relation is epsilon times L. What is exact is that I'm also able to tell you what is the prefactor of the third order structure function, which is 4/5. And the other thing you should see, which is again quite remarkable, is that there is a minus sign. The minus sign in front of it is an indicator of the fact that the energy is getting transferred to smaller scales. All right. And how you do it is via what is called as Karman-Hoover-Monell relation. I won't go into details about it, but one good place to look at all this stuff is this book by Uriel Frisch called as Turbulence, and I encourage you to have a look at it. Okay, so with this quick fire introduction to turbulence, by the way, whatever I've told you, there are many wrong things in it, because I have told you that it's self-similar. In reality, thanks to again Frisch and Parisi, we know that it's not self-similar. There are corrections to it. But for what we are going to talk today, it's okay if you think turbulence is self-similar. All right, and that would be fine. So with that, let's go ahead and let me introduce the problem to you. So the problem that we are interested in is very simple. These are industrial applications, bubble column reactor, but the application which should interest you a lot is this much. Like every day morning, you wake up, you take a pot of water, you start to boil it, and immediately start that the bubbles are rising through the system. And you could ask yourself the following question: is it good to have bubbles, or is it bad to have bubbles? Right? You could ask whether bubble enhance energy transfer, whether heat transfer, whether presence of bubble enhance mixing. How does all these things happen? Similarly, you could also see bubbles in fish tank. So why bubbles are there in fish tank? Because you want oxygen to get mixed in water. And again, you could ask the question, does it help mixing of oxygen in water? How efficient is it? How do I understand this mixing process? And there are several examples of these kind of things. And so indeed, it's not only me, but there are several people who are interested in understanding this phenomena. And one of the simple ways you can think of it is the following: that as these bubbles are rising, you can think of them as particles. They are moving through the fluid. So as a solid body moves through a fluid, it generates a wake. The wake of one bubble will interact with another bubble and would create a complicated mess. And that complicated mess, we would like to think of it as turbulence. The question is it the same turbulence that Kolmogorov and others were thinking about? Or is it a different kind of turbulence? Or are there regimes that in one regime you have one class of turbulence, in another regime you have a different kind of turbulence? Does surface tension play any role in this system? Remember, there is a large density contrast between bubble and water of the order of 1,000. So should I think about this system as compressible turbulence? But remember, the Mach numbers and everything is very small. So most probably its divergence of velocity is 0. So there are lots of interesting questions which you can start to ponder about. And this is what we started to think about. And so let's go ahead. Now the experimental systems where one looks at this are very simple. You have a tank. and then you let the bubbles go through, right? And then as the bubble goes through the system, it generates some flows. And then you have to be smart enough, which most of the experimentalists are, to track put in particles and then to track the particle trajectories and then reconstruct the flow. And if you can reconstruct the flow, you can understand more or less everything about the system, right? And indeed, there are groups of Detlef in Puente, Andrew Bragg in Duke, and Tianma in Johns Hopkins, who have been looking at these problems for quite some time. But if you are someone like me who is slightly less sophisticated and can do numerical simulation, then you do the same thing on a computer. You run the system with bubbles, generate some kind of flow. And the advantage then you have when you do numerical simulation is that you have flow field at all the positions. So you can understand the statistical properties maybe a bit better. And then check with experiments or even tail experiments that, look at this particular regime. And then if your experimentalists are your friend, they will look at the regime and then you can learn more things. Now, one of the things which I would like to emphasize that as a fluid dynamist, one should always look at the non-dimensional number or dimensionless numbers which are. So the system we are looking at, namely bubbles in water, there are three numbers which are crucial, right? The bubbles are rising because of buoyancy. So one of the dimensionless groups you could think of comes from the ratio of buoyant or from the balance of buoyancy forces to the viscous forces. That's your Galilei number. Okay, this is equivalent to a Reynolds number. The other number is the ratio, how deformed the bubble can be. Well, that depends upon what is the interplay between the buoyancy forces and the surface tension. That's your bond number. The third non-dimensional number which is relevant is what is the density ratios between the air and water. That's the Atwood number. For a realistic system, or maybe I shouldn't say realistic, but for air-water system, Atwood is 0.99999. All right. And then there is viscosity difference. So, but that, at least for the parameter range we will be working on, is not so relevant. But these three numbers are very, very crucial. And what one would like to understand is that is the energy transfer or the flows that are generated in these systems, are they independent of Atwood number? Do they only depend on Galilei number? Do they depend on bond number? And what is the mechanism of transfer? And finally, there is a crucial thing which I haven't pointed out here, but I should, is that I'll think of the system in the regime where bubble-bubble interactions are on. There are no direct bubble-bubble interactions. That is, bubbles don't bump into each other. I'll work in the regime where bubbles don't break apart. And so the only interaction between bubble is via wakes. So the wake of one bubble interacts with the wake of another bubble. The bubbles can deform, and this is a cartoon of that. All right. So one is working at low volume fractions in that regime, and this is where most of the experiments are also. All right. So as I mentioned, this is an old problem. Already people in France, in I think Marseille. Yeah. So the Reynolds number is same as Galilei number. So typically the square root of Galilei is the Reynolds, and one easy way to see it is that this particular term here, delta rho GD, or the velocity of the bubble is delta rho by rho GD cube, square root of it. You multiply it by the size of the bubble divided by the viscosity, you get a Galilei-like number, square of. Okay. So, people were looking at this problem since 1991. And these were the initial results by Lance and Batal. And they came up with a very, very simple idea that energy is, so as the bubbles are rising, they deform, generate wakes. And these wakes are immediately dissipated in the vicinity of the bubble. Now, when I make that statement, there is no question of cascade. There is no question of surface tension. I'm thinking of it as a very local process. A bubble is rising, generates some wakes, and this wake gets immediately dissipated. And then they had a simple argument which says that the viscous dissipation therefore balances the energy production by the wake, and that is given by epsilon omega by k. And you balance it and you get k raised to -3. And indeed, when even the group of Lotte and others did their experiments, found that there is a good evidence of -3 scaling. And then the question is, okay, so the problem is solved. There is nothing left to do. And yes.
The data or what?
Okay, so the black colored
That's
data
the data.
is the, no, so the black colored curve is the energy spectrum of forced homogeneous isotropic turbulence. You shouldn't see the black colored curve,
Okay.
or you should not look at it. The blue colored curve is the one which is for bubbly flows.
And that's experimental.
And that's experimental. Both these are experimental. And then this is the -3 scale. Okay. And of course, then everyone said that the problem is very simple and the Lance and Batal argument holds. And, but then as a physicist, you should always ask what happened to surface tension? What happened to pressure fluctuations? This particular assumption that things are quickly dissipated always assumes that the time scale of dissipation is much smaller than the time scale of buoyancy production, which is much smaller than time scale of nonlinear transfer. Is such a scale separation in time or space present? And so these were all the questions which we were worried about. And just again for the students, to emphasize that surface tension could be important, here is a simple exercise that you could do. You could ask yourself the following questions: that if I take an interface and assume that there is a vortex, which maybe is generated by some other bubble, comes and hit this interface, how would this interface evolve? You can actually solve this and consider this as a long Lambert-C vortex. You would see that it would form this kind of the interface over time makes this kind of a structure, which is called as a little spiral. And what you can then do is that take your Navier-Stokes equation and take a curl of it. So if you take the curl of the Navier-Stokes equation, something which comes up is that, so there is one term missing, which is the vortex stretching. But apart from that, what I would like you to see or appreciate is that there are these extra terms, which is grad rho cross F, which is the gradient of density multiplied with the surface tension, and another term, which is fairly common in astrophysical MHD flows, comes out as grad rho cross grad P, which is nothing but the baroclinic torque. And this again becomes important because you're working with variable density system. And then, of course, similar contribution from viscous dissipation. So the thing which I would like to emphasize is that even in a simple system, it's very easy to appreciate that if you have a density contrast and an interface, you could have vorticity generation mechanisms. On the other hand, the simpler explanation by Lance and Batal completely ignored all these things, right? So then you would like to understand, okay, so are all these things relevant or not? And the first attempt of this by simulations was done by Irene and Detlef. And what they did was they took point particles which were rising under buoyancy, and then they found something which was unfortunately not visible here, but maybe is visible over there. What they found was something which is completely different. They found that there were initial indications of, in 3D, something like an inverse energy transfer, but on long time, everything died. So they were not sure what's happening. And then there was the group of Greater Trigvasan. He did some simulations of bubbles rising through a fluid, but at very, very small Reynolds or Galilei. Okay, these are extremely small Galilei number, and they found a scaling of -3.6, which is not -3, but it's close to experiments. And then they said that, look, what is crucial is the fact that bubbles generate wake. And these wake flows are the ones which are driving the fluid. All right, so then the question was again, all right, if this is true, can we do simulations now in 2020 or 2025 where we can match exactly the experiments? All right, so that was our aim, and then understand things. And then as a physicist, I was very upset with this problem. The reason I was upset with this problem was that in physics, typically you want to make general statements. You want to make statements about systems which are true across Atwood number, which are true for a large range of Galilei numbers. On the other hand, if you talk with the practitioners of the field, they wanted you simulations or all your analysis at Atwood 0.999. And so the thing was that, all right, so let's try to understand, but I can do whatever I like. So I said, let's try to see if if I do bubbles at different Galilei numbers, are there any difference? So here is a study of experiments of isolated bubbles which are rising. And you see, as you change the Reynolds or Galilei number, the flow structure around the bubble changes, right? The shape of the bubble changes. So you might agree with the general perception that to understand the physics, you indeed need to hit very large Galilei numbers, right? And air water is crucial, right? If you were, let's say, doing alcohol in alcohol mixtures, maybe the physics is completely different, right? And then while I was giving this talk somewhere, K.R. Srinivasan told me that he was involved in this experiment and this picture is wrong. The flow is not as it looked like, it's very laminar. So then again, it wasn't clear what's up. So anyways, we went ahead and we said, let's solve these equations, right? Worst come worst, what's going to happen is that we'll say, so how do we solve? We have Navier-Stokes equation, where now density is a function of composition, right? When you are in bubble, you have one density. When you are in liquid, you have different density. Viscosity also, in principle, is a function of composition. And how you evolve bubbles? Bubbles are evolved as a front, okay? And this front is moving through the fluid, is interacting with the fluid. The front can deform, and as it deforms, it modifies the fluid in the vicinity. All right. And how do we solve this? There are two regimes in which we work. One is like good physicists, we make Boussinesq approximation, do a pseudo-spectral solution of the Navier-Stokes equation. And for high density difference, we use Paris, which is a code by Zelinsky and Tigwason, which is a finite volume. And for bubbles, we use front tracking algorithm. So these are fronts which are moving through the fluid. And this is fairly standard. And this is what the picture looks like. So if you have, so we took the same exercise as in the experiments, small Galilei, small output, the bubble just makes straight rectilinear motion. The flow is very, very simple around it. You then go Galilei 420, the bubble starts to oscillate and the flow is different. Now the wakes are getting shift. This is just the Z component of vorticity. That's it. You do Galilei 360 output 0.9 and bubble starts to dance and makes a horseshoe vortex structure. Now you ask yourself the question that if I take, let's say, a suspension of this bubble and a suspension of this bubble, what is it I'm going to get? So that's what then you do. You do a simulation first for a single bubble like this, and you see as the time evolves, the bubbles start to shed wakes, and these wakes then start to interact with each other, create some kind of a soup. You can do the same thing with the other guy. And again, somehow it's running a bit slow, but you see that it again makes jelly. Yeah.
Force this.
No, because there is gravity, right? So the bubbles are rising because of buoyancy. So there is no external forcing. The system is churned because the bubbles are lighter than, right? And then you get this kind of a mess. Now a question. Are the statistical properties of this mess identical to this mess? That's the thing which we wanted to check. And remember, the two are at very different output. This is output 0.04 and this is output 0.9.
Right. Why is the Galilei different?
Oh, because I wanted to do a scan.
How?
Right. And when one says that large, it's not clear what is large, right? So is 300 large Galilei number, is 1000 large Galilei number, is 10,000 large Galilei number. So you want to scan. So and that's what I did. So you vary Galilei number, right? And then you vary output number and do the studies. And but what is crucial and what comes out quite nice is that irrespective of your Galilei number, okay, if you look at the PDF of horizontal velocity fluctuation, normalized of course, they fall on, at least the code falls on top of each other. Much more interesting is that these triangles. The triangles are experimental data. So the experimental data falls on top of the numericals. And the experimental data is of course at output 0.999, the viscosity contrast is 100, whereas the simulations are from all the way output 0.04 to output 0.9. Okay, and looks like at least the core of the PDF is correctly reproduced, right? And then of course you expect the Z component of velocity to be asymmetric. because as the bubbles are rising, they drag the fluid along with it. And indeed, the core of the PDF is consistent with experiments. We believe that these departures that you are seeing at large um, velocities are because the wake structure, you can now feel it and they are different, right? But the core is very similar. You can also look at the center of mass velocity of the bubble, but more interesting, wow. The most interesting is the spectrum. Okay, so when we did first study, it was at 0.09. And what we found is that as the Galilei number is increasing, the spectrum seems to be approaching the experimental spectrum, which is k raised to -3. And then referees being the referees, they said, no, you should do simulation at large output number. And at that time, the only study which was available was from that left group, which was in frequency space, and compare your data with output 0.997 and show that it's agreed. Then we did that. That's thanks to the hard work of Vikas, and we showed that it agrees. And then there were simulations which were followed by others, Innocenti et al. And others, which were at 0.99 with mesh refinement and whatnot. And everyone seems to be falling now on the same set of data. So it looked like that, irrespective of the output number that you have, right, you are able to recover the -3 scaling, which was observed in experiments. All right. And yes. Sure. So output number is the difference. So output is defined as so let's say rho liquid, rho bubble, rho liquid plus rho bubble. So when I say low output number, the difference between the liquid density and bubble density is invisible. And where can that happen? If you are alcohol in alcohol mixture. On the other hand, if you go to air water, then your output number is very large. It's 0.99. Okay.
What about the bubble concentration?
So it's very small. So the volume fraction of bubbles is 0.1%. But these bubbles are fairly large. You're talking of millimeter size bubbles.
Small enough, obviously, to get that, but non-bubble problem.
Of course.
That works.
No, what do you mean by non-bubble problems?
Well, you have one bubble
Yes.
in a vast tank. It's not going to make that much difference.
No.
So
What do you mean by it's not? But then, if you have only one bubble, then there is not going to be hydrodynamic interaction.
yes.
And
I'm
that's
wondering where bubble concentration comes into your picture.
because of the simple fact that the only interaction between bubbles is via hydrodynamic. If you, let's say, kept on increasing the volume, you will go to a regime where bubble-bubble interactions themselves will start. The bubble collision will start to come in. And I'm in the regime where I'm ignoring it. So you could, in principle, draw an axis where you have volume fraction, and you could go, let's say, less than 1%, and then you are in the regime of individual bubbles. Right? And here you won't see any of this phenomena because each of the wakes is more or less independent of the other. Then you are in the regime of 1 to, let's say, 6% or 7%, where only interaction between bubble is hydrodynamic.
You're in that picture.
I'm in that region. And then you could go even higher, and then you get into the dense emulsion kind of thing. And that's a very different. It's like as you go on cranking it up, if you go all the way to, let's say, 97, 98%, then you get into the regime of 4. And then that's yeah. So in this particular case, so we define here or we prescribe the cyclic bubble. But what your question is most probably the following: that I can't choose any arbitrary size bubble because eventually, as it's rising, it will form a break. So the number that takes care of it is the bond number, which is the ratio of surface tension to viscosity, and the bond number that buoyancy to surface tension. Bond number is typically less than 5 or 8. So you are in the regime where the bubble doesn't.
So, somewhat similar vein, perhaps. This discussion is entirely in terms of the K spectrum stuff. Could you imagine a problem in the expansion of the bubble cloud by wake-wake scattering? From the point of view, the bubble makes a wake, the wake
Yes.
scatters the neighboring bubble, etc., and the cloud will expand much the same way a turbulent wake will expand. And that clearly can happen. The
Yes.
question I'm asking is there some sexy scaling law to be had out of that?
So that's an interesting question. Honestly, I haven't thought about it, but it's worth looking at. I agree that you take bunch of bubbles, and as they're rising, you ask how does the bubble cloud expand, and is there a simple scaling relation which can explain the expansion of this bubble? Yeah, but I haven't looked at it. At least right now, we are in the regime of homogeneous suspension. So, but you're right. That's a very interesting question. Yeah. Okay. So now we have all of this. You could ask the question then that, so our earlier studies were motivated by experiments. And most of the experiments were at Galilei number 800, 600. And then we said, as we are doing numerical simulations, no one stops us from hitting higher and higher Galilei. Right? So then we did that, rather Vikas did it, and we keep on cranking up Galilei number, and eventually you get to a state which looks very much like turbulence. And then you ask yourself the question, okay, what do I expect for the spectrum now? Do I expect again -3 all the way? Or a 5/3 scaling appears? What is it that I would do? And so we did what, because we can't do a massive simulation. What we did was we took all our data, put it all together, and did a standard turbulence scaling. So on the vertical axis is suitably scaled energy spectrum. On the horizontal axis is k eta, and all the data collapses onto, let's say, somewhat on a master curve, where the places where these curves are going off from the 5/3 are, so this is roughly corresponding to bubble diameter of each of the runs. So we do see inertial range 5/3 scaling appearing, which I pointed out to you earlier. And then it crosses over to something like the -3 scaling and not the viscous scaling. We don't know what happens at very small scale because we don't have resolution yet to look at that. But it appears that at sufficiently large Galilei numbers, you could have Kolmogorov scaling reappearing, and this then Kolmogorov scaling crosses over to something of a -3 scaling, which was observed in earlier experiments. And the question was that whether any experiment would ever be able to see this. So I sent a mail to my friends in Johns Hopkins, Tian Ma and Andrew Bragg, and I said, look, we have found this. Is there a possibility to, and Chao Soon, is there a possibility to do an experiment? And they did it. And they found Kolmogorov scaling. And what is the fun is that they were able to fine-tune the experiment in such a way that they were able to maintain large enough bubbles that do not break. And they found out that close to getting 1,000, they start to see a 2/3 like scaling. And what is more crazy is that as you try to increase the bubble diameter, then it starts to break apart. So you are not able to achieve higher and higher Galilei numbers. Now, again, one can't rule it out because you could do some experimental trick to get even higher bubble. But at least there is some preliminary indication from experiments that whatever we were proposing of a possibility of seeing Kolmogorov scaling in these bubbly flows is not ruled out. Yes.
What is the crossover scale and what is your injection scale?
So good point. At this point, the crossover scale is defined in an ad hoc way by something like a Kolmogorov scale, right? So you just say it's nu cube over. So you assume the phenomenology of homogeneous isotropic turbulence to be true, although you understand the flow is not isotropic because the bubbles are mostly going in one direction. But as the quantities that you're looking at are all isotropic, you invoke that phenomenology and you say that, okay, there should exist a dissipation scale. And we know, thanks to Modin and Yaglom, that dissipation scale typically starts to kick in around 0.3 eta. And indeed, you start to see that this crossover is happening around 0.3 eta. So, but that's very ad hoc. Huh? I mean, I don't have. You could ask me why surface tension is not here, and so I don't have a clear understanding of it yet. No, so it's at very preliminary stage at that level, but that's a very valid question. Yes.
Where is water bubble radius?
Good point. So the 1 over bubble radius, because as I mentioned, there are multiple runs at different Galilei number. So you see each of these curves is crossing over like this flat. So that's the bubble radius here. So one radius here, one radius here, one radius here, it's going up. So what we did was we did simulations with different either gravity, because we can put in the value of or different buoyancy, or bubble diameter. And then you take all your data for different Galilei numbers, which range from 100 to 2057, and put it all on a single plot. So they're similar to what one used to do in old days for homogeneous isotropic turbulence or grid turbulence, where you had experiments at varied Reynolds number, and then you would put all those experiments on a single curve to see whether you have 5/3. So it's exactly the same exercise. Sorry? So it's fundamental in determining what is the injection scale. It is that this rescale or this graph which I made here, the rescaling is done with the dissipation scale. That's why the injection scale is varying. And that's what would happen also in any grid turbulence data, that the injection scale would show up at different level if you are normalizing it with the dissipation scale. Yes. No, it's excellent.
Did you try to fit an exponential like
We did. And the exponential, so what we did was we took Johns Hopkins database, which has extremely high Reynolds number data and large K data, and then that thing falls off much faster. So we are very sure that it's not. So I can show you the plot later. It's very, very clear that it's. Yeah. Okay. So how I'm doing in terms of time? 10 minutes or 15 minutes?
Don't worry. In some sense, questions are buried in some of the questions.
Excellent.
So just keep going.
Okay, good. So all right. So now let's ask ourselves the more detailed question. How do I explain the origin of -3? Yes, Lancer bata raha hai. How do I explain the origin of -5/3 scaling? And when I say explain, again, this is going to be something which is numerics aiding some analysis. And I won't claim or even dream of claiming that what I'm going to tell you is a theory. Okay, so let's start by looking at small Atwood number, which is where the density contrast is small. In this regime, the equation simplifies. What you can do, in the standard Business-like regime, you can ignore the variation of density in the inertia term. The only place where you retain the variation of density is in driving. That's what you do. And then the equation is simplified because you straight away see that now you don't have any baroclinic torque. Because if you take the curl of this equation, the pressure goes off. All right. So you already see that making an assumption of small Atwood number or Business regime is something different than large. But okay, maybe the term which is important is subdominant, but we'll see later. And then what you do is something which was pointed out, I think, day before yesterday in your talk, which was you do a LES-like analysis, where what you do is you do a filtering of your flow field, define large-scale fields, and write down the effective equations for energy transfers. Now, if students are not able to get it, that's fine. I can discuss this in more detail in the discussion session. But what you end up getting is something in the steady state. The nonlinear flux plus the transfer because of the surface tension is balanced by viscous dissipation, injection due to buoyancy, and if there is any stirring, but there is no stirring. So nonlinear transfer plus surface tension transfer, the transfer mechanisms, is balanced by viscous dissipation and injection by buoyancy. Okay, and this is the kind of curve you take. So let me take you over this curve. So remember, when you do a scale by scale budget, all the quantities that you get are cumulative. So what do I mean by that? So if we look at the green curve, This is the curve which tells you about the injection up to a given scale. It's not injection at a given scale, but injection up to a given scale. So if you wanted to find out what is injection at this scale, you have to take a derivative of this curve. All right. So if you take a derivative, you clearly see that most of the injection is taking place around the bubble diameter, which is all right. So this is the curve which shows you net injection. This is the curve which is showing you dissipation. And now already you can see at odds with Lance and Basal, there is a separation between injection and dissipation. If Lance and Basal was completely accurate, then injection and dissipation should have lied on top of each other. But there is a separation here. And what is controlling this separation? One, the blue curve, which is the nonlinear flux. This is the energy transfer because of the advective nonlinearity. And the surface tension. So what's happening is that as the bubbles are rising, they absorb energy and they pump it back into the fluid. Now, crucially, if you say, I want to stick with Lance and Basal, you can define some net production as sum of surface tension plus nonlinear transfer, and then you get this particular curve. And you straight away see that this curve has a scaling of log k. But that is expected, right? That's what you would expect from dimensional energy. And that is balancing viscous dissipation. So you can do a balance. You take a derivative of flux, the net production, which is phi of k plus f sigma, and that should be equal to viscous dissipation, thereby giving you the -3 scale. Okay. So this at least explains that even though Lance and Basal are not completely correct, if you, let's say, rethink of what the production could be, then you can put things together and you understand what is the origin of -3 scale. Then you go ahead and you ask yourself the question, okay, what happens at still low output number, but I crank up the Galilei number? Remember, in this regime, you again expect -5/3 scaling to appear, because -5/3 scaling appears at large Galilei number, irrespective of your output number or density flux, and then you straight away see when the nonlinear flux starts to become dominant here, right? You have a strong nonlinear flux between ranges, which correspond to the bubble diameter, and it crosses over to some scale which is roughly around theta. And in this regime, then, because the nonlinear flux is dominant, you expect 5/3 scaling. And then after the crossover, the sum of these two again is close to log of k, which then balances viscous dissipation to give you -3 scaling, right? So that's the simple explanation. But then you go ahead and you say, now I want to explain the final thing, which is energy transfers at large output number. This is where life becomes complicated. Why? Because now you can't ignore pressure. And there is a very good article by Aitke and Rivas on understanding energy transfers in compressible flows. And this is also very relevant for astrophysical MHD. And what is one of the most interesting things is that once you define or look at variable density, you can actually define infinitely many, not infinitely many, at least 6 or 7 definitions of energy. So you could define it as filtered momentum times filtered velocity. If you're a physicist, you could define it as filtered momentum times filtered momentum divided by filtered density, which is called as the Fourier filtered energy. And both, and or you can define another definition, which is filtered density times filtered velocity times filtered velocity. Keep on coming up with combinations like so, right? And you could then ask that, are all the definitions equivalent, right? Yes. Okay, good question. Once. You see, we are interested in understanding energy transfer across scale. So if I want to do that, I want to then define what is energy at a given scale. How do I define energy at a given scale? I want to then know what is the density at that scale, what is the velocity at that scale, what is the momentum at that scale, and based on that, I need to define the energy. So when I say energy subscript k, which means energy at length scale, which is roughly k inverse, okay, and that is equal to momentum at this scale multiplied by velocity. right? But you could say why you want to define it like this. Why don't you define it as density at scale k multiplied by velocity at scale k multiplied by velocity at scale k? A friend of yours might say, look, you guys are all gone mad. The right way to think about it is momentum square times density. So we should define it as momentum at scale k multiplied by momentum at scale k divided by density at scale k. And, come up with someone could say, oh, no, I want to do, which is very famous in astrophysics, square root of density times velocity at scale k multiplied by square root of density times velocity at scale k. And that's why I said you could have infinitely many combinations, right? You could say rho to the power 1 over n u of n, keep on saying that. And you see, each of the cases, you can write down a scale by scale budget, which is fairly easy to. And the reason I pointed out this paper is that this paper claims, through nice arguments, that if you are doing very compressible flow or high Mach number flow, then this particular definition is more favorable. But that claim is only true if your flow is not incompressible. That is, if your divergence of u is not equal to 0. On the other hand, for us, we have a variable density flow where divergence of u is 0, right? So that thing goes out of picture. And so all these definitions are equally good or equally bad. And now, like a good movie, what I'm going to do is I'm not going to tell you anything about this. And I'm going to tell you, look at my paper. But I'm going to only concentrate on this particular picture because it makes you easily understand what's happening. And that's where more or less I'll stop. So if you do that, then what you find is something very interesting. You find that, okay, there is an injection happening. There is dissipation happening. That's all right. But there is something remarkable. You see, now the fluxes are starting to rise before the injection scale itself. What's happening here? And that's because it so happens that in these systems, pressure leads to an inverse transfer of energy to mass. So when I first time saw this, I was completely baffled because you typically don't associate transfer with pressures because one is conditioned to think of deeply compressible flows or incompressible flows, which are constant density, whereas in variable density, pressure fluctuations are variable. Okay, especially at high atom count. That transfers energy to large scales. There is then a transfer of energy to small scales by nonlinearity, right? And the surface tension does it part. And still because you have a strong nonlinear transfer to small scales, you end up still getting minus 5/3. Things which we are exploring, is there a possibility to make, at least numerically, a system with bubbles rising or in other variable density scenarios where you could have extremely strong inverse pressure transfers, right? If we could manage to do that, then that would be a very interesting system. And then one could, maybe allure experimentalists to look at it in more details. But that's what we have. And I think with this particular message that, there are differences between low output number and high output number, although in your small scale statistics, you might not see them. In the fact that there is a mechanism which hasn't been looked at in so much details for the kind of flows I was looking at. But then I figured out that people who do very high Mach number variable density flows, they have alluded to some of these things in their stuff, right? So the pressure can do a transfer, and depending upon the scenario you're looking at, it could actually be forward or backward. It's a priori not clear. In the bubbly flows that we are looking at, the numerical evidence shows that it's transfer to large scales. And that's where I will stop, and that's more or less the message. And if some of you are interested in understanding, can I talk about the same picture using physical space velocity correlations by Harman-Holt-Monin relation, or what happens if you look at different definitions of energy, this is the paper. So this is where I'll stop, and I think I've more or less covered whatever I wanted to talk. Thank you.